Okay, so far in our little universe, we've been looking at position, and if you recall, we have our friend, the x-axis, some arbitrary but uniformly spaced units on it. And we have our body B, which is sitting somewhere on our x-axis. And we'll call that place where it's sitting x0. And we talked about what would happen if B was changing its position relative to time. And we call that a delta in x over a delta in t, change in position over change in time. And we decided that we'd call that velocity. And for the instantaneous case of velocity, we would call that dx dt, where this represents a derivative or a differential of x with respect to t. Then we said, well, okay, what if v is the thing that's changing? And so we looked at delta v with respect to t, and we decided that that was called acceleration, and that for instantaneous acceleration we would look at dv dt, the derivative of v with respect to t. Going back to this equation here, we can see it follows from this equation that dx equals v dt. And we can look at this equation from which it follows that dv equals a dt. So starting with this equation here and integrating, we have the integral of dv equals the integral of a dt, from whence we get v as a function of t equals at plus some constant, which we call the initial velocity, v0. And then again, going back to this equation, we do the same thing and we say that the integral of dx equals the integral of v dt. And if we substitute this value in for v, we find that x of t equals the integral of at plus v dt. And then if we take the integral of that, we get 1/2 a t squared plus v naught t plus, again, an arbitrary constant, x0, which is our initial position, which we can see right here. V naught is a constant, x naught is a constant. So this is sort of the generalized equation for position of x with respect to acceleration. So if we know the acceleration, and we know the initial velocity, and we know the initial position, we can always determine the exact location and position of x. And I just wanted to put this equation down because in the earlier video we did go through an example that did this, but I don't think I ever actually wrote the equation down. So what can we figure out about movement based on this equation here? Well, we know if t equals 0, then x of t equals just x of 0, because you have a 0 here and a 0 here. And we knew that because x of 0 is our initial position. So if we're going to move B, at the time we start moving B, t equals 0, position of x, or I'm sorry, the position of B is x of 0. If acceleration equals 0, then x of t is just b naught t plus x naught, or x of 0. Remember, these are constants. So this means that with no acceleration, x is moving at a constant velocity from some initial location. And we can also say then, well, what if initial velocity is equal to 0? What if v naught is equal to 0? Then x of t is simply x0. You're not going anywhere. If you have no velocity for all time, your position stays the same. Where do we get a velocity from? What makes B actually move? We know how to describe it if it's moving, but we don't have anything yet in our universe that causes it to move. Let's say that we have B, he's sitting here on the x-axis, and he's sitting at position x naught, x of 0, and he has no velocity. So we can go back to this equation here and substitute those values in. And just for simplicity's sake, let's say that he also has no initial position. In other words, x of 0 is equal to 0. So we're going to redefine our number line so that he's sitting here at position x equals 0. So he's sitting there and we want to make him move. Well, how do we make him move? He has no initial velocity. V sub 0 is 0. X of 0 is 0. So if we look at this equation, then we end up with x of t equals 1/2 at squared. So the thing that's going to move x is acceleration. We know from up here that in order to get a velocity, we also need acceleration. Velocity equals acceleration times time. Acceleration is the key here. And acceleration is nothing more than the result of a force acting on a body.